I'm Lluís Galbany from Barcelona, from Institute of Space Sciences at the SIC. And actually, this talk would fit better yesterday in the distance ladder section or session, because I'm basically talking about type 1a supernova distances in the near infrared. So just put your brain in the yesterday session. We are back to distance ladder here. Yeah, so we have talked about type 1a supernova these days a bit, but no one put you this slide, the first slide that you should put when you talk about type 1a supernova, because although we have been using them for decades to measure distances, we still do not have a very precise picture of what is going on in the explosion of these stars. We know that they are white dwarfs in binary, as I said, probably with three stars as well. And we know that what is exploding is a white dwarf, an old star, but the progenitor system may be a single degenerate with a massive star, a double degenerate, core degenerate. The explosion mechanism can be a detonation, a deflagration, double detonation, merging of two stars, surface explosions with helium. I mean, there are Chandrasekhar mass explosions, sub-Chandrasekhar mass explosions. There's a variety of things going on. And most probably is a mixture. What is going on in nature is that there's a mixture of these scenarios and explosion mechanism. But anyway, observationally, and I'll talk a bit about this, we have been using them as precise distance indicators. This is how, well, the distance model expression, we just measure the apparent magnitude, and we assume that they all explode similar. This is what is a standard candle. As we will see, is standardizable, but anyway. And the assumptions, there are two assumptions here, is that there's no evolution on this. So supernova at low redshift are the same as supernova at high redshift. And what I mean here in same populations, this is a bit not very precise. What I mean is not that the same they are the same populations at low and high redshift, because we know, because galaxy evolution, that these change, the ratio of populations change. But what I mean with this is that a supernova with younger companion is the same at low redshift and at high redshift. Nothing has changed. So the model is the same and works at all redshifts. So what we do is get the light curve. This is up here on the left. And we parameterize this light curve, getting the peak magnitude, some measurement of the width of the light curve, or brightness decay, if you like. There are several parameters that do that. And we can, from the multivariate light curve, we can plot the color curve down here, and we get an estimate of the color at peak. These are the three main parameterizations. Here you see the Phillips relation and the, well, color relation. It's I didn't put the original references here. This is called the Phillips relation from 93. There's the Rees 96, Tripp 98, Burns 14 for the color relation. This is from the ES, I mean, just a random sample that I use. And you can see the absolute magnitude relation with measurement of the width and the color. So this basically gives you, or is a proxy of this progenitor scenario explosion mechanism. What is the progenitor mass? I talk about Chandrasekhar and subchandra. All these parameters relate a bit on all these physical things. And also, there's in the color case, there's also an estimate of the extinctions suffered by this explosion. So this is how we parameterize these objects. Here I put before the distance model expression. What we do is to add these two empirical correlations, one with width, one with color. And then we have our cosmological model, our preferred cosmological model. Well, there's the distance, the luminosity distance. You have your cosmological parameters, and then you just feed your model to the data. This is an example from the ES, 3 years. It's not the most updated one, but it's the one that I had in these slides. You can subtract this observation to the model, and you get the Hubble residuals, which is the bottom plot here. And you see here different models, and one fitting better than the others, in particular the one with dark energy. So this is not new. from the 2010s, 3 papers by Mark Sullivan, Pat Kelly, and Hubble and Patel, found that these residuals, actually, there's some dependence still, besides those 2 empirical correlations, in the 3 cases, on the mass of the host galaxy, but now we call it in the environment. So there's some environmental dependence. And this pointed to a 3rd empirical correlation that includes any parameter that has to do with environment. And here is the same sample where you can see the stretch against mass and the color against mass, and you see that there's some differences at low mass values and high mass values. So this was found in the 2010s, but this has been found previously as well, not on cosmology, but on observational parameters of supernova against host galaxy properties. Actually, this was my PhD thesis. This is a very old slide that ended in 2014, but there have been lots of more works putting more constraints on that. So we go from extragalactic astrophysics, supernova progenitors, environment, dust, through this expression to cosmology, and this is another example from Pantheon plus the Hubble diagram. And what this allows us is at low redshift to constrain cosmological parameters, H0 and sigma 8 in this case, and at high redshift the components of the densities and in this case the equation of state of one of the parameters of dark energy. So we are interested in systematics. This is just a very simple slide where I colored each of the correlations and just, not random, but some examples. This is not the only thing, but for instance, the stretch may correlate or may have information on the progenitor, on these different progenitors that we talked about before. I put an example of Ginolan, very recent from ZTF, that instead of a one linear relation between magnitude and, in this case is the Hubble diagram, the Hubble residual, sorry, and the stretch, there's this broken alpha relation that may give you an idea of having 2 populations there. For dust, there's a lot. Ariel is here. His group has been working a lot. I just put here from Chris Barnes the Snoopy paper, and you mentioned this in Geza's talk in the question, that we actually find when we feed all these parameters, and for supernovae we found lower RV values than those found in the Milky Way. So around 2. RVs are around 2. So there's something that we can understand here or try to find out about dust properties on supernovae. And this would, of course, introduce systematics in the distance measurement. On the right, I put some plots from Miquel Rigol on the environments. This is a very nice paper from 2013 where they look at the environment, but not at the global parameter like the mass, but at the position of the supernovae. So here, this is something related to Hubble diagram against mass, but the colors depends on how intense is H alpha emission at the position. So star formation, active star formation at the position. And you can find the colors, I didn't put the legend here, but basically white and blue are one population that have active star formation, and those in gray are the passive environment. So you may see that that relation with the environment may have to do with other parameters in the environment. In this case, that environmental work was focused on local parameters. So there have been more things that, of course, will introduce systematics also in the distance measurement. But this is, I'm not sure if you have seen this strip here saying optical all the time, but here I'm supposed to talk about near infrared. So supernova in the near infrared is not a field, not a field, but there have been studied since the 80s. And these are 3 historical papers by Elias, the first, where for the first time, let me take this out, I cannot read, but anyway. For the first time, they claim that the light curves in the near infrared of supernova 1A were actually very similar. In the second paper, also by Elias in the 85, this is the paper where it was proposed that type 1 supernovae may needed to be split in 1A and 1B. So 1B is a core collapse, and 1A actually show a very homogeneous light curve compared to 1B, and also mentions that in the near infrared they were more clear. And then in the 2000s, Miekle already said that they could be better distance indicators because as I will show later, the light curves were more homogeneous and the extinction at those wavelengths is reduced, so there's reduced systematics. So that's the promise of the near infrared. Light curve corrections, the three that I mentioned before, are smaller than in the optical. And this is a plot by Chris Barnes in 2018, where on the bottom plots, you can see SVB, which is a stretch color parameter, and the stretch delta M15. In the V band, this relation between magnitude, absolute magnitude and stretch, which is what I showed before. And on the upper plots, in the same relation in J and H, which is flatter. So this means that this empirical dependence is lower in the near infrared. Also in the near infrared, as I mentioned before, is much reduced compared to the optical. It's just 20% in H compared to V. And as said by the historical papers, the light curves, these are just normalized at peak. These are not standardized. These are, as they are seen, they are more uniform in JHK, YHJHK bands. So that's the promise. Sorry. And these are so then with that promise, people have been trying to use them to measure H0. So you see the reference is 2018 by Chris Barnes as well, and updated last year by Shubo Udin. They have been using template fitting, the same template fitting that we use for the optical. So there may be some corrections here. They used 15 in 2018, 20 in 2024 calibrators, supernova calibrators that were in supernovae that were in SHUS calibrator galaxies, but with near infrared data for the supernova, and about 100 or 200 in the Hubble flow. These are the one plot from the paper. And I will extend later on this paper by Suhail Lawan from 2018 that used J-band interpolation. So no corrections at all, just the observed light curve. Of course, this is, for that you need, as I will show later, better light curve, more cadence, and you should be able to interpolate at peak. And there were only 9 supernovae in calibrator galaxies and 27 in the Hubble flow. This is a plot on the right from that paper, and they provide an estimate of H0, all these papers. So the uncertainty in H0 with 36 in this case in Suhail paper is comparable to 200 in the optical as for SHUS, for instance. So the point is that the systematic effects are reduced because there are less parameters. You don't have those terms that may introduce systematics, and as it has been said for 3 times already, the extinction is reduced at those wavelengths. So with this in mind, we had that paper in 2023 where we basically updated this work by Suhail, basing our sample from the RIS 2016 sample from SHUS to the updated on 2022. We went from our initial sample from 19 to 42 calibrators, and also we increased, we did a sort of search in the literature for Hubble flow supernovae at high redshifts, of course. We also include H-band. That previous work was only in J-band. We corrected photometry to put it in the same system, something that you have to do to get at least, even when the data has been observed with different telescopes, we want to have all the photometry in the same system. And as Suhail did, we didn't use template fitting, just Gaussian process the light curve, as you can see here in these 2 examples, and just get the peak magnitude in J and H. So these are the calibrators. As I said, we went from 9 to 19 in J in the updated sample, and also we include H, where we get 16 of the 42 calibrators with near infrared light curves. In the Hubble flow, from 27 originally, we were able to to include some more, to 52 in J and 40 in H. You see the scatter is, well, comparable to 1A's in the optical with the standardization. This doesn't have any standardization. This is the peak magnitude as it is, 0.15, around 0.15 and around 0.1 in H. And then, yeah, we put all together in the machinery with this likelihood here to measure H naught. So the absolute magnitude is given by the calibrators, the intercept is given by the Hubble flow data. You put all that together, and our results are up there, 72.3 basically in J and H, with a statistical error in this case of 1.4, 1.3 about. And a sigma of 0.12 and lower than 0.1, sigma intrinsic scatter. So then we, for estimating the systematics, we performed up to 21 variations, including template fitting, only using data from CSP, from different surveys, CSP, CFA, changing the peculiar velocity corrections, changing the redshift from different sources, only those that were in galaxies with lower Milky Way extinction, changing the Hubble flow cut, things like that. And we got a dispersion of 1.08 kilometers per second per megaparsec. And to this we included other systematics that came from the anchors, because we are using Schuss distances for C-fates. So these are the systematics of the anchors. 0-point photometric 0-point systematic, and uncertainties related to the peculiar velocity corrections. So all that in quadrature sum up to 1.4 kilometers per second. Then we tested, as I said, this doesn't include any standardization, but we tested what would happen if we include these optical corrections here, in particular that related to the stretch up there and to color down here. And as you can see, the slopes of those relations in J, which is in red color here, they are reduced compared to the optical, as you can see on the bottom. A slope in B of 0.6 here is about 0.1, and in H is basically flat, mostly flat in both cases. So when we include the corrections, and even including both corrections, the H naught value doesn't change that much, by 0.1 or so. But what is reduced is the intrinsic scatter in J from 0.12 to 0.9, and in H doesn't change that much, just a bit, because as I said, the slopes of these relations are basically consistent to 0. So this is our final result with the systematics included, 72.3 plus minus 2, more or less. This is lower than 3%. So this confirms that 1A in the optical are not the problem of this Hubble tension. So this is one of, well, it's not the problem, but one of the problems of the Schuss measurement is that the C-phase distances are measured in the near infrared, but the supernova data is in the optical. So this is a full distance ladder in the near infrared. And in order to improve this work, we can either increase the number of calibrators, which it has been mentioned as well from ZTF, and in the future with LS4, we can include different calibrators, not just adding them to the 40 in Schuss, but doing the analysis independently. For that, we will need HST and JWST data. We can increase the number of well-observed Hubble flow supernovae. Right now, about 50. We had 200. We may reduce the uncertainties. And we can further test this standardization in the near infrared. And for these improvements, we are working currently on the environment, including environmental analysis in these near-infrared distances. We started this project, FLOWS, that already has about 800 supernova in the Hubble flow, but this is a technique that uses a single epoch around maximum. Since the light curve doesn't change and doesn't need corrections, you get one point about around maximum, and you use that as a distance. And then SAINS is, I put here just a near-infrared 1A Pantheon-like. So we are working on compiling the whole thing available in the near-infrared. We have more than 1,000 objects. We would like to repeat this kind of analysis with this sample. Very briefly, because I have 5 minutes just for the talk, right? Not for the questions. Yeah, so plenty of time. So I'll talk a bit about these 3 points right now. So for the environment, in the past we started these 2 projects, PISCO and Amusing, that are obtaining integral field spectroscopy of host galaxies of supernova. PISCO is with, the instrument is PIMAS in Calaralto in Spain, and with for Amusing we use MUSE at Paranal in the south. This is north and south, so the characteristics of the IFS are different. But so far, well, these are examples of the data. This is SDSS image, and this is how H alpha map, intensity map looks like for PISCO and Amusing. Of course, the spatial resolution is much better for MUSE. It's an H-meter telescope. It's deep, it reaches deeper surface brightness. But the problem of MUSE is that it doesn't have the blue so far until blue MUSE arrives in a few years. So with that, we already obtained more than 1,000 supernova host galaxies. Lots of works are going on. We have more than 40 papers published, but there are a lot more going on. But the relevant thing for here is that we include all the SHUS galaxies. So there's a work going on about estimating local metallicity for C-fates, but in this case, environmental properties, local environmental spectroscopic properties of SHUS calibrators. Flows, this is a project that was funded for a few years, where basically we get data or discoveries from ZTF and also optical light curves, full light curves. When this is very early and is classified A1A, we trigger our resources to get a single point of our maximum in J and H. I only show here H, but it's in J and H. And with that, the goals will be to increase by a lot, the number of objects available for the Hubble diagram to measure H naught, and also do some work on peculiar velocities to estimate sigma 8. So this is based on a simulation we published in 22, where this is one single supernova in lots of bands, in particular J and H. Yeah, this is G and R, the same that ZTF will give you for free, and J and H. And what we do is to simulate that what would happen, what would get in the near infrared if we only have one epoch in the near infrared. And this is a video that you will see that the optical the feed doesn't change, but the near infrared feed changes depending on the epoch of that plot. If you put all these feeds together, you see that when around maximum, there's a lower scatter of the feeds. I mean, those feeds that you see very far are those that are used, those done with data farther than 10 days or so. This is a summary plot, and you see that the scatter about around 10 days from maximum is much lower compared to later. So these enable the flow survey, and so far we have 760 supernovae with a goal. Probably we won't reach that, but by 1,000. And we are obtaining one for a few only. We have 2 or 3 epochs, and this is the coordinate distribution of this sample. So there's a PhD thesis going on, and there's some people already in Aarhus and Barcelona working on this data. Finally, that's my last slide. I didn't see if it was 2 minutes or 1, but that's the last slide. These are the suspects, the saints. This collaboration that we started with, I forgot to put the affiliations here. Eric is at Duke in Durham, North Carolina. Joel is in Stockholm. Thomas was a postdoc in Barcelona, now in Dublin. With that, Matt and Aaron as well are postdocs in Cambridge. And Suhail is recently a professor in Birmingham. With different experiences and approaches, we have put together this more than 1,200 data, all available in the near infrared, up to 0.7. And we are starting from scratch, from the light curves, doing the recalibration of the photometry, using different light curve filters, Snoopy, SALT, and BiasN, doing a systematic analysis of the host, global and local properties. And the idea is to do something like Pantheon Plus, but in the near infrared. And we will then have different studies, focus studies of several things. So one including one H0 measurement with all this data. So I think, yes, that's my last slide. Thank you very much.
Thank you.
Very nice, Luis. I was wondering,
What's the current situation with calibration in the infrared filters? How good are the flux standards and all that sort of stuff? In the past, it used to be a problem. I don't know if that still is.
Yeah, there's this something that in particular in Saints, Aaron is in charge of this. I mean, you have to find someone that likes calibration in all teams. So my understanding, because I'm not one of those, but my understanding is that there's cal spec standards that can be used now and then do some kind of, because you are aware of this, but this is the Boki thing that Brody Popovich is doing in the optical, but this can be done as well in the near infrared with this data. I don't know the details, but it's true that in the past that there have been these problems, and in particular when you see the systematic analysis we did, when you use CSP and CFA separate, this is the largest difference that we found in each node. So it goes down to 71 and goes up to 75, when you use only CSP and only CFA, and this is just because the transmission of the filters are quite different, even when you try to correct that with a simple S correction. But that's one of the goals of Saints, going to the observed data and doing all the steps one by one and putting everything in the same system in this particular case.
Thanks again to the speaker.